You're listening to a Pop House Network podcast for developers by developers. Welcome to the Java Pop House episode 103. Hey everyone, my name is Freddie. We have been taking a really long hiatus on the Pop House while we were just trying to, we went through a couple of years of COVID and stuff, and we were like a little bit burned out. But you know what? We took a big break. We are rested and we're ready to really rock it out of the ballpark. And we're going to start covering the new things, because while we've been snoozing, the whole world around, our industry is changing, right? So we not just that we want more new versions of the language, but there's also like large language models, there's like analysis, there's big data that is coming in, and there's like the performance that needs to go with it. So we'll be starting to cover getting some guest hosts to come in and talk to us about like the projects they're working on. And this one is, we're kicking it off. It's going to be a very fun one. For those who are listening for the first time, my name is Freddie Guime. I am one of the co-hosts of the Java Pop House. I'm a speaker, Java champion, Seattle Java Users Group co-organizer. I'm a distinguished principal engineer at Expedia Group, always wondering about that performance angle that we have for it. And I'm here with my partner in crime, Bob.
Hey everybody, Bob Paulin, independent consultant from Chicago, Apache Software Foundation member, Java champion, and CJUG board chair.
And today we have an interesting and awesome guest, Matt.
Hey, I'm Matt Topol. I work at Voltron Data. I am author of currently as far as I'm aware, the only book on Apache Arrow. I'm also a PMC member. Yep, and I gone a while back, gave him a signed copy. But yeah, I'm also a member of the Apache Arrow's PMC. And for anyone who's not familiar with Apache Software Foundation parlance, Project Management Committee. And at Voltron, my day job is I work on the Arrow libraries. So I have the rare situation of being able to get paid to work on open source software.
You are having fun. This is great. And if you haven't picked up the theme of today, we're going to be talking about this amazing columnar in-memory library called Apache Arrow.
But the one thing to think about is that it's a format spec.
Interesting. So it's almost like
there's a big separation to keep in mind with Arrow. Is you've got Arrow, the format, the spec, and then you have Arrow, the project, which is essentially just a collection of implementations and utilities surrounding that format.
So that is almost like the JSRs, the Java specification documents where you define this is a spec, but then everybody else is free to implement that. And as long as you follow the spec and pass in the compatibility, then you can use it, right?
That's the entire intent. So to kind of give like the basic introduction, as you mentioned, Arrow is a columnar in-memory data representation format. It's a format spec for how you can represent hierarchical or flat data in memory, column-oriented fashion. And it's laid out in memory identically, regardless of what language or library or wherever you're using it, so that the data can be easily shifted around and used interoperably without, overhead costs and serializing or deserializing.
Got it. And then before we dive in, the last thing I wanted to do is before we can actually just geek out, because I have 100 million questions about this. We wanted to thank our sponsor. Today's show is sponsored by Datadog. a monitoring and analytics platform that integrates with over 450 technologies, including AWS services, Docker, and Kubernetes. Datadog's platform brings together metrics, traces, and logs in one place so you can get full visibility into your environment and improve your application performance. With machine learning-based alerts, customizable dashboards, and distributed tracing, Datadog makes it easy to unify disparate data sources so you can troubleshoot faster. Start your free Datadog trial today. Listeners of this podcast will receive a free t-shirt once you install the agent and create one dashboard. Visit javapophouse.com/Datadog to get started. And again, that URL is javapophouse.com/Datadog to actually download and install the client. We like to thank them for allowing us to essentially keep the cameras, the mics on, the cameras rolling, and the beers flowing as we record this episode. So please give them a shot. In your project, they do integrate with a bunch of like different kind of services, and as a natural customer for them, it's super nice. So we thank them again for being a sponsor, and give them a shot. Datadog, javapophouse.com/Datadog. All right. Let's get to the meat of this. All right. So tell me more, man. Like why would I use Apache Arrow? Like, so we first discovered, there's interop, right? Just because, there's a spec and anyone can import. Well, as long as you follow the spec, then anyone can interop with these, right?
There's implementations for Arrow in ridiculous number of languages. There are official implementations of Arrow in C++, Java, Python, Go, C#, Julia, MATLAB, Rust, Ruby. There's more that I can not remember.
Nobody implemented
like 12 or 14 languages that have Arrow library implementations.
Yeah, did somebody implemented it in Perl? Hopefully not.
I don't think so, but we just
No, that's it.
That's a contribution opportunity for anybody that wants to do some Perl, right? I mean,
so most of the interpreted languages are implemented as basically a thin wrapper over the C++ library.
Right, that makes sense.
Like PyArrow uses Cython to create Python bindings against the C++ Arrow library. Same thing for Ruby using glib.
Right, and Java's kind of interesting because they have it where it's like, hey, there are JNI bindings on a lot of the libraries, but there's also, hey, you could be reading from native buffers using the Java NIO libraries, where it is more pure Java as well.
Exactly. In general, the Arrow implementation for Java is pure Java, but it does have some JNI bindings for dropping down to the dataset library and exposing some of that compute functionality that the C++ library provides. They expose it in the Java library via the JNI bindings. And the important thing is, once again, because Arrow's format is independent of the language, it's the memory layout is identical in those. That means that the actual cost to get your data from the Java memory and use it in C++, there's no serialization or deserialization. It's zero copy. You're passing pointers in both directions, just passing pointers and a little bit of metadata.
Yep. And that's like the geek out point that we want to get to. But let's put it together. Let's zoom out a little bit. So you look across the ASF landscape, and one of the things that you see in the foundation is a ton of data science, right? So you've got databases like Cassandra, you've got Spark for compute and aggregation. You've got, you got a Hadoop for storage and Iceberg and all of these projects. And some of them are Java, like a lot of the ones I mentioned are Java, but then you've also got a lot of data sciencey stuff that's happened in Python, where they're using pandas and PyTorch and TensorFlow. And all of these systems, they all want to move data around. It's probably slowing a lot of things down. Is that kind of like where you see Arrow is the magic that solves this problem?
That's exactly the idea there. So, Arrow the Arrow project started around 2016. It was co-started by Wes McKinney and Jacques Nadeau, Wes McKinney of Pandas fame, and so on. And it came out of the idea of the Hadoop ecosystem where large, enormous amounts of time, of processing time was spent just converting data from one format to another as it went from one system to another system. Like you would take your data that's in memory over here in this system, and you want to send it there. Okay, so you're going to convert it to protobuf to send it over there, and then deserialize the protobuf to use it in there, and then then the output's going to get converted to JSON to send it to that system, and you're spending 90% of your processing time is just serializing and deserializing data.
Right.
And so Arrow, the concept of Arrow actually originally grew out of the Apache drill value vectors, which was Apache drills, which is a distributed compute engine.
Yep.
Was using this columnar, format internally as its in-memory data representation, and the idea was to kind of expand on that and make a standard. And suddenly, when you want to take your data from this system and send it to that system, well, if the bytes in memory are exactly the same to represent the data in both sides, you can just shove the bytes across the wire and not have to pay any overhead of serializing or deserializing. And that's what Arrow grew out of. And so Arrow defines a whole bunch of data types. You have your fixed width types, your int 8, int 16, uints, floats, all your normal, what you expect from your fixed width types. But then you've got your variable length binary data, you've got string data, you've got lists and hierarchical types, you can represent struct arrays, unions, so on and so forth. And Arrow's just grown since then.
Yep.
So you can represent any kind of tabular data that you want using Arrow.
It's interesting because like when you start thinking about it, right? Like you have your internal structure, your model, and this model has a certain representation, and translating that to a different model from a different OS or a different stuff, there's a penalty for you to essentially read from your model, write it and in a transferable format, and then essentially deserialize it, put the bytes where they belong, which are going to be different places because it's just
because different programming languages represent structures in different ways.
Yeah, so this is interesting because essentially the backing store of your model is already on the format that can be read from this. It's almost like the backing store for every language is going to be the same. So that's
the intent.
Yeah, so there's this, you lose the need to do this translation of like, oh, Java has a 16-byte header for these things and a string header for this. It's like you kind of create your model on Arrow, and then that in itself, as long as you read from that model and write to that model on Arrow, you immediately guarantee that you can then read it from another, just ship the construct, read it from another place. So
a great example that I can give that will probably resonate with your listeners is Spark. So there is an option, there's a config option for Spark to tell it to use PyArrow if you're using PySpark. And what is important about that is if you consider how interacting with PySpark and Spark goes, if you're in the Python side and you read in a 5 gigabyte CSV into a pandas data frame, and you want to send, and you want your Spark process to process and use that data, well, that means that you've got to take your data frame, and the PySpark JPipe connection is going to have to serialize all that data to send it to the JVM,
Yeah.
The JVM will then run your Spark, do your thing, get your results, whatever. And then it comes back and goes, okay, now I have to serialize that result,
Yeah.
send that to Python, deserialize it, and then do a thing.
And then garbage collect all the objects it created in that process.
Exactly. Or, here's the fun part. So Pandas actually does, the Pandas 2 has a, and Pandas has a Arrow based backend you can use. Which means that you can take that 5 GB data frame as Arrow and pass that to Spark across the JPipe thing without any serialized or deserialized cost. You just hand it pointers to the data and a small bunch of metadata. The JVM takes the pointers. They're just pointers. You can access the memory directly.
Yeah. So I'm missing.
It can do whatever it wants to do.
Yeah.
Get the result. And it doesn't have to serialize or copy it back over the Python. It just creates small little structures that populate the pointers of where the data buffers are and a little bit of metadata of the types and stuff, and then hands those small C structs to Python.
It knows how to read it.
Which can then interpret the data. And when those structures are garbage collected by the Python interpreter, it calls a callback to tell the Java side, I'm done. You can get rid of this now. You know, and that's what we call the C data interface. Because it's a very small set of structs that are designed to not change. So they are ABI compatible everywhere. You have an ABI stable C struct header that's intended to be vendored or copied into your projects. And you use those to communicate across a C boundary. And all you're doing is you're populating a bunch of pointers and some metadata. You know, the length of the array, how many nulls are in it, so on and so forth.
That is so funny.
And because Arrow's column oriented, because as we've seen with a lot of analytical stuff and the OLAP and everything going on, column oriented memory or processing gives a couple really big benefits. Most processing in an OLAP or analytical space, as you guys are probably familiar with, is very much processing one or a couple columns. You're processing the whole column. You're not typically doing row at a time.
Yeah.
Which means that if your data is organized in the traditional row, format, you have to jump around in memory to process a column. But since Arrow is organized as column-oriented format, you're going to benefit from the CPU caches. You're going to benefit from the L1, the L2 caches, because it's going to grab the cache line, and the next value it needs is right there in the cache line because it's a column-oriented memory.
Yeah.
Which also means you can benefit from SIMD optimizations, and the other vector optimizations, compilation, vectorization, so on and so forth.
Yeah, no, and I think let me dive into this a little bit because it's such an interesting world. Like the very first part is if you're dealing with significant data, right? Like you are really dealing with large data sets. Like it's one of those things where I did not realize how much time you spend, first of all, just reading that. Like you need to like I remember I thought that I had like and this is just a fun experience. Like I like so I'm reading like all this like essentially airline data. Right, it's terabytes of data about like all the different ways they can charge their customers, right? It's like, it's crazy. It is terabytes, and I'm reading it, and I'm deserializing it on the CSV, and I'm looking at it, and I see my heart, like my disk reads just drop, like, I have like a on my computer, there's like a gig backplane and stuff like that, and it's SSD and all that. And I'm like, oh, I'm not even hitting like the max that I can. And I'm like, wonder what's going on. And when you look at it closely, you start realizing that it's the freaking actually reading and deserializing that is taking the actual time. So
Mhm.
so to the point where it's not even an I/O operation. It was like CPU bound from like trying to create all the memory objects and reading it out from disk,
Oh
right?
yes, CSV handling, absolutely memory, absolutely. Like, well, it's, if your storage thing is fast enough, like an SSD, then you're absolutely going to be CPU bound on that deserializing. Absolutely.
No. So the first thing I was like, yeah, for everybody who's out there listening, if first of all, if you're dealing with large data, this is a problem that, and you're like running into performance issues, or even if you don't, because like everybody charges by the CPU now. So just optimizing on performance, you're essentially getting money back, right? Um, that's the very first part. Is like make sure you measure, because most likely than not, large data sets you start paying your price in serializing and deserializing. Now, for the second part, you're talking about like, and this is fun because it's like SIMD, and then we're gonna go into SWAR, but what does that mean? So there is this concept like called mechanical sympathy, right? Like Martin Thompson was one of the, I don't want to say the first one who came up with the term, but at least is one who advocated the most.
Okay.
And the idea is that you try to work in a way that is friendly to the architecture that you're
Yep.
running your software in.
Yep. Exactly.
Right, like I think the term originally was like came in from like racing cars, and it's like almost like it's not just that the racing car is all of them are the same. Like everybody's a little bit different. Like
Yeah.
sometimes let go of the gas, but you're shifting. The other ones you have to shift faster. Like and said like the mechanical sympathy was the term that they told the drivers like they needed to learn how to operate that machine at top notch. So one of the things that you're describing is that it's essentially bringing mechanical sympathy is this idea of what is called cache locality, right?
Yep. Memory,
And
memory locality and cache locality.
right, and the idea is it's super simple, right? If you think about it, you get the CPU, and the view that we have about this, like in 1978, right, was like before there were caches, right? You have something in main memory, and you're like, I need to do something on main memory. So you go bring up the value from main memory, put it on a register, bring another value on the main memory, put it on the register, and do some operation, right? And then once you're done, you write it back to main memory. Now, this is in the I think what is the access time for main memory now? 100 milli it's at least 100 nanoseconds.
Yeah. Yeah.
Retrieve time.
Let's see here. Okay. Main memory access latency commonly.
Yeah,
Here that's a mega. Is here DRAMs with 70 nanosecond latency.
got it. And
Modern DDR4s have a latency of under 15 nanoseconds.
Okay. Yeah.
oh yeah,
Significant.
yeah. But it's like so what happens is that sounds very fast, right? But when you have to read this all the time, especially if you're processing something very large, then that kind of like kind of trips you over because it's essentially you'll see and the effects are hard to see because you'll see that your CPU is at 100%, but everything moves kind of slower than they could really be. And this is for the second part, which is the cache locality. The thing that happens is that chip makers decided that, look, every time that somebody reads something from main memory, chances are probably like 75% that they will want the stuff that is next to the stuff that they just read, right? So they're like, oh, let's say, for example, that you're reading a value, right? Like you have an array of integers, right? And you're reading like the first 4 bytes of the integer, and you're processing that array on a loop, right? Then chances are that you want to read the next 4 bytes to do like a sum, right? Let's say you're doing a total, right? So what a lot of chip makers did was like, all right, instead of every time that they read from main memory just to go out there, let's essentially read the stuff that we need to read. Plus, let's fill it up to like 4 kilobytes or whatever it is right now. I think L2s get to 8 kilobytes. L1s are still smaller.
Let's
I think last I heard, the most recent processors had an L2 cache upwards of 128K.
Oh God. Okay.
So it's a lot. So there's a lot to fill in. So you can guess wrong.
I think the L1 caches are like 60 or maybe like, I don't know, 16K or 64K. I don't know. It's been a bit.
But it's a lot, right? Like if you think about like we're talking about like, even if it's only 8K, it's 8,000 bytes, right? And an integer is like 4 bytes, right? So what happens is chip makers said, like, we're just going to read the rest of that, and we're going to call that a cache line, and we're going to put it there. And the next time, like, as your array keeps going, and it's going to say, oh, now I need the next bytes on my memory. And the CPU will say, wait a minute, I read those. I have them here.
We guessed right.
And it's an order of magnitude faster. Like I cannot clarify. Like going to main like, even though main memory access is extremely fast right now, compared to actual like cache L1 or L2 cache,
you're looking at like for the L1 cache, you're looking at like 1 nanosecond or less to access it.
Yeah, it's an order of magnitude faster, right? So then what happens is, imagine this, right? Like it's, you start reading and then you're doing this sum on this array and then getting every byte and then adding them up, right? You go from spending even like 20 nanoseconds to go to main memory to like, oh my gosh, now only once every, 1,000 reads, I need to go back to main memory to get the next cache.
Cache miss.
Yeah.
That's when
and that's where the thing is, like, where you're doing a column-oriented representation lets you take advantage of that. Mm-hmm. It's because the traditional way of laying out, a table of data is is in a row way, where you have pretty much the array of structs versus struct of arrays is the common way of referring to it.
Yeah, that's an interesting. Yeah.
Traditionally you have an array of structs.
Yep. Yeah.
To represent a table, as opposed to a struct of arrays, where each array is a column, as opposed to the arrays being the records.
Yep.
Right. And
Arrow takes advantage of that and leverages it. And you were mentioning the larger data sets. So the communication format, Arrow defines a inter-process communication, IPC description. And what that format really is just a very small flat buffer header, and then just the raw buffer bytes. It's just the buffer bytes for all the buffers back to back with a small header top. Now, this gives there's two really good things about this. The first is it's really, really easy to stream it. It's great, simple, easy to stream. It has its own MIME type. There's a registered MIME type for Arrow.
Oh, that's amazing.
Arrow IPC streams have their own MIME type. But so it streams very well, and it's very nice that way. But it also can be written to disk as an Arrow file, or it's also called a feather file.
Mm-mm.
And going back to what you mentioned about dealing with large data sets, if you have the Arrow data as an Arrow IPC or feather file on your disk, the bytes, the buffer bytes, the data bytes are still laid out in that file exactly as they would be in memory, which means you can mmap it, you can memory map the file. And it's only ever going to try to read or access the data from the disk when you try to access it.
Yep.
There's no deserialization cost, which means that it's very, very efficient to manage a larger than memory file.
Yep. It's turtles all the way down, right? So you've got your processor with it lined up. You've also got your page cache is the same thing.
And so, and I mention it because if anyone's dealing with like LLM or other machine learning stuff, they might be familiar with the company Hugging Face.
Yep.
Hugging Face is very big name in the data set providing and stuff like that. Well, Hugging Face data sets leverage that quality of Arrow IPC files.
Oh,
Hugging Face data sets are Arrow IPC. On
really?
disk, it's an Arrow. On disk, it's an Arrow file.
Oh, that's fun.
So that they can memory map it to only allocate memory for the bits they need. There's some examples on their documentation where they process the entire Wikipedia data set, you know, the 18 gigabyte, whatever, and it only ends up costing them maybe 100 megs of RAM.
Yeah, and let's talk a little bit about what that means. So, I mean, when you're talking about a memory mapped file and only using the bytes you need, you know, the OS level, you have your user space memory, and then you have stuff that's managed by the operating system that can be shared, right? I mean, it's
exactly.
So your page cache is part of the OS,
all the way down to the kernel page cache.
Exactly. It's cached, and it's not user space memory. It's there to be shared. So if you've got a program, and especially like a Java program where you have to set a heap, and you're trying to understand your memory optimization. The idea that you would have to have all of that in user space means you have to have heap allocated, you have to have allocations and ability to have that. If you keep it in the kernel space, like you look at your program memory and it's not taking up that gigs of however much that file is. It's only the small amount that you're using at that time in the program.
It's mapping the size of the file to a virtual memory space. And whenever you whenever you try to read a specific section of the file, only at that point, which from the perspective of your application, you're just trying to access this address in memory, effectively.
Yep.
But because you've mapped that address to the file, at that point, the kernel OS level, system goes, oh, I need that section of memory. Well, that's a mapped file. I need that offset into that file. And then it reads a page worth of data. Commonly in OSs, that's like a 4K.
Yeah. Exactly.
4K on the page size. Sometimes they might do 8 or 16. But, it reads that much around the spot you try to access. But from the perspective of your application, you can address anywhere in the entire file. So you can have, a 20 gigabyte file.
Or a terabyte file.
Or a terabyte file.
Yeah.
Yeah. And it costs you no physical RAM until you try to actually access it.
Yeah. And
by address. And typically the problem with memory mapping is that generally you're not going to save that much in a lot of cases, because even after you map that, in most cases, you're going to have to decode or deserialize or otherwise that data into something you can operate on. But with Arrow using Arrow as that on-disk format, you can pull in that piece you've mapped and operate on that as is without needing that extra copy.
Right. That's the Arrow libraries, right, that you're bringing with you, is because it's been the code's been written to understand the format and either use the compute or
because the
filtering. Yeah.
Because the bytes on disk are exactly what it would expect to exist in memory.
Right.
And because you do the M mapping and it uses pointers, you get the full representation of Arrow representations of your data of that entire humongous file, but it never actually takes up the physical RAM until you try to access the buffer.
And it's interesting because it's worth like highlighting. First of all, this is not like you need to, for Java developers, which is probably 95% of who listen to us, right? is this is not something you need to like even set memory for, right? Like the interesting part is this is a kernel slash OS feature. Memory map files is supported on like essentially the major OSs, and they take care of figuring this out for you. Like there's like and they take it they are very well optimized to
I
read.
will say there are caveats to this. This is not your solution in every scenario. There are caveats to when you may or may not want to do it this way.
Why don't we talk about some of those then, Matt? So like you know, large files versus small files is maybe one of those spots
Yeah,
where maybe
yeah.
there's a difference.
So I mean,
that.
memory mapping in general, has some drawbacks. And generally, the trade-off you're trying to figure out that you're working here is going to be I/O performance or not, because so standard I/O without the memory mapping, you have the system call overhead, and then you have the copying from the kernel buffer into your
user space. Yep.
That's the and you're going to have, and so when it does that, you have your costs for page faults and stuff like that.
Right.
When you do a memory mapping, the first time you try to access that memory spot, you've basically pushed the cost off to the point where you access it, rather than being, I've read everything I need, and then every time I try to use it, it's already in memory. No more, I don't have any page faults. When you memory map, you're going to have a lot more minor page faults, because every time you try to access that spot or another area of the file, it's going to, at that point, it's going to stop and do the I/O.
Now, is that with a lot of random access? Like, again, like when we're talking about the processor with the columnar data, if I'm scanning and I'm going all in line, is it the same cost in that case versus random access?
The costs are different. In the case when you're doing like a memory map file, say your cache line is 64K, okay, but your page size of the buffer, the kernel page buffer, is 4K.
Yeah.
When it tries to read that data, it's going to read from the file for each page.
Yep.
It didn't slurp the whole thing into memory and pay that one cost of pull all of this into the kernel buffer, copy that into main memory, now access it. It's got to do that virtual translation of the addresses. But the data stays, but you still get to bypass that copy into main memory,
right?
Because what you get back is a reference to the kernel buffer memory. So that's the trade-off there. The other aspect there is that memory mapping tends to be less scalable because of the page faults. If you're going to need a large portion of the file at one shot,
might as well load
maybe better to just read in what you need rather than memory mapping.
Yep. And let's just talk real quick about page faults, if that's a new term for people. So when you're reading from disk and something is already in the page cache, that's all good, right? That happens very quickly. But when you read from an area that's not there and actually has to hit the disks and get that off the physical disk and pull it into the OS, like that is when you have faulted. It didn't, kind of like the CPU guess and pre-read that section fast enough. I have to wait, do a hardware thing, and then
operating systems can be sneaky.
Yes.
That's because
sometimes it's trying to do a smart thing too, right?
Just because it says something's in RAM doesn't actually mean it's in RAM.
Yeah.
Because you get the page swapping and and the caching and the it's gonna you loaded this into memory. It's in memory, right? Well, no, I wrote that to disk to make room for that thing over there, and now you wanted that again. Well, now I have to go pull that back in. Yeah. Operating systems are sneaky like that.
No, and I agree. Like there are knobs that you can turn. Like like first of all, like if you're doing like memory map files for large data sets and you have almost like a sequential access to it, chances are that memory maps help because your overhead of how much main memory you need to use at a certain point in time is very low.
Yeah, it's actually interesting because it's slightly counterintuitive that the faster the faster the actual device is, the worse the overhead of the faulting is going to be. Because, and the reason for that is because on a slower device, it'll the cost of the I/O is much, much more than the cost of dealing with the page fault. But
Right.
because memory mapping can significantly increase the number of page faults, if your storage device is super fast, you're going to be paying a higher cost in all those page faults than if you just read the data in.
That's an interesting one. That's almost like if you have something that reads almost as fast as main memory.
Exactly. So that's it's scalability. The other thing is you don't really want to use memory mapping for small files.
That we can all agree on.
Well, do you guys know the reason for that, though? Reason why that's a bad idea?
I can imagine, but it's mostly that you are like you're first of all, if your file is smaller than your page, you're still reading your page.
Exactly. Exactly. When you do a memory map, every access to your file is going to be page sized.
Doesn't matter if your file is 10 bytes or
exactly. So if you're doing memory mapping and your files are fairly small, you're actually going to end up using more memory than you needed to because everything still has to be page aligned.
Right. And if you're using huge pages or some other kernel toggling, like it can get worse, right?
Exactly. So memory mapping really, really helps for accessing, if you need a subset of data from a really super large file, memory mapping is amazing.
That's how you call it.
Like if you take if you take this enormous 100 GB data set and you wanted to just calculate the sum of a column, mapping that file, if it's written in with Arrow, means that you'll only ever need the amount of memory to hold the single column you needed, rather than needing to read the whole file in.
Yeah.
So it's trade-offs on trade-offs on trade-offs. Where's your bottleneck? Is your bottleneck I/O? Is your bottleneck memory? If your bottleneck is memory, just read the whole. Then mem mapping might be a good idea. If your bottleneck is I/O,
read the whole thing.
Mapping is not necessarily the best idea because now you're going to be doing more I/O potentially, depending on what you do.
Yeah.
So that's kind of there. And so you have the IPC format that I mentioned. And the other things that we build on top of that, and where Arrow excels again, is we're talking about network traffic.
Okay. Let's hear now. Let's turn the page into how do I distribute this then?
What was that?
How do I distribute this over the network?
Yes, yeah. And so that the IPC format I mentioned, like I said, small flat buffer metadata followed by just the data, and that's one message of the IPC stream, and you send a stream of these messages that are flat buffer header, blob of bytes.
Right.
And the first message is always a schema message because these things are self-describing.
Oh, that's nice. So you don't have to worry about like having a contract somewhere. You just
the first message of the stream must be a schema message.
Got it. And it
describes the schema of the data that you're sending on the stream. And every subsequent record batch message, a record batch in this case is what we refer to is what generally is referred to as a batch of records. Think of it if you take a table, it's just the top 10 rows of that table as one contiguous thing.
Mm-hmm.
That is a record batch.
Mm-hmm.
And then and then the next chunk of rows is a record batch. So if you have a large amount of data, you send it in chunks
Right.
as a stream of record batches.
Mm-hmm.
And the way that these are organized, essentially, a record batch, every column of the record batch is a contiguous chunk of memory for that column.
Mm-hmm. Mm-hmm.
And if you say take those arrays, you can take the individual columns and view them logically as one big table without having to actually copy and concatenate them.
Right.
And a lot of the Arrow libraries have a table abstraction, which essentially is just a logical view of a group of these record batches.
Mm-hmm.
You can treat all of it as one big table, even though under the hood, you've got, it's being represented as a series of chunks so that you don't have to pay that overhead of having to actually copy everything and concatenate every time you read the next record batch in.
Mm-hmm.
So building on that block of using the Arrow IPC streams of data,
Mm-hmm.
the Arrow project developed what we call Arrow Flight, which is a gRPC framework for sending Arrow data as a service. And building on that framework, there is the very poorly named Arrow Flight SQL. I say it's poorly named because really it's just general, any kind of database system interactions. Arrow Flight SQL is great for it.
Yeah.
And so, like, for example, Dremio implements Arrow Flight SQL. InfluxDB implements an Arrow Flight SQL server.
Oh.
And it's a spec. It's a protocol spec. Any server that implements the Arrow Flight SQL interface can be accessed by an Arrow Flight SQL client. And for example, there is a JDBC Arrow Flight SQL driver where you can have a JDBC or ODBC driver that can connect and query against anything that exposes an Arrow Flight SQL interface.
And you would not know, you wouldn't be the wiser. Like behind the scenes, you don't know that you're running into Arrow because you're just using JDBC as your abstraction.
Well, the reason why that matters is because performance across the wire. Traditionally, ODBC and JDBC are very row-oriented protocols.
Right. It is true.
And so what ends up happening but modern OLAP and analytical databases are increasingly becoming more column-oriented internally.
They are.
And so you end up with this situation where you have a column-oriented database that then converts and transposes all that data to rows to send it across the wire because of ODBC and JDBC. And then you read it out of ODBC and JDBC on your side, and then you convert it back to columns to do your analytics locally.
Oh.
But if it's Arrow the whole way through, well, if you're using the ODBC or JDBC Flight SQL driver,
you're going to get it out, and then it's going to be
sending it. Yeah. But the Arrow IPC does allow for compression at a per buffer level if you want.
Oh, nice. Yeah.
And so one nice thing about column-oriented data is that it compresses super well.
Because the data around the columns is very similar.
Because exactly that, data of the same type compresses much better than data of varying types.
Oh, that's fun.
And you can so just switching to Arrow Flight SQL, people have seen 10, 20, 100 times speed ups for the wire network cost.
Yeah, and that's kind of like the second cost that people don't consider. Because like when people are sending stuff on the wire and because it, it magically appears on the other side, sometimes you never look at the payload.
Yep.
And
And the thing that they really don't consider is that transposition cost that I mentioned. And I bring this up because, as I said, you have Arrow Flight SQL, you're getting the wire better, but now you're still converting from columns to rows at the other end, right? Because of ODBC and JDBC. Or there is a DBC.
Arrow DB. Oh, so
Arrow database connectivity.
all right.
Arrow database connectivity is, just like ODBC or JDBC, a defined API spec that you then have drivers implement. So your application codes against the ADBC API, which is Arrow native. Everything, all the data comes through ADBC as Arrow record batches and streams of Arrow record batches. And then you swap out the drivers for whatever you want. And for example, there is a Flight SQL ADBC driver.
Okay.
So anything that interacts, that has a Flight SQL interface, you can just use ADBC with and get your data. But then, say you're going across the wire and doing ADBC and Flight SQL, but now you want to use DuckDB.
Okay.
Well, okay, your application code doesn't change because DuckDB implements the ADBC API.
Really?
Yeah.
DuckDB
implemented ADBC in the actual libduckdb.so. So the ADBC libraries have driver managers, and you can just load libduckdb as an ADBC driver, and now your in-process ADBC queries just go straight to DuckDB, and you get Arrow data back out. And you get to benefit from zero copy because DuckDB's internal memory format is essentially
files.
very similar to, if not identical to, Arrow.
I see.
And DuckDB uses that C data interface I mentioned for C APIs to pass Arrow data out into and out of DuckDB so that you don't pay a copy overhead.
And that's interesting because so essentially the ADBC API, it has also a corresponding ADBC. I assume there's like an Arrow SQL language then, right? That you can
just like ODBC or JDBC, ADBC doesn't specify the SQL language or anything about the dialect.
Interesting. Okay.
The SQL dialect is based on whatever you're sending it to.
I see.
There's a function, set SQL string.
That's whatever it is.
And ADBC as a spec just says, I take this query and I send it to the driver and say, here's the query that they made. And then the driver and the database interpret that however they want.
Got it.
ADBC doesn't specify the dialect, just like ODBC and JDBC don't specify dialect.
Interesting. Yeah, that's true because ODBC and that's every different engine it has a little bit of their own.
Exactly.
Yeah.
Of course, then you can, if you're playing with Python, you can use IBIS to help with that, but that's a different argument we can play with. But yeah, so like right now there's ADBC drivers for Snowflake, Postgres, SQLite, Flight SQL, DuckDB, all have Google BigQuery, all have ADBC drivers that you can load. There's the Java client for your listeners. There's the Java driver manager. But the point is that anything that implements that C API spec can be used as a driver. The spec says data is returned as Arrow.
As Arrow, yeah.
What will be the Arrow friendly or the most Arrow native engine for ADBC?
I mean, well, it depends on what you mean by Arrow friendly, Arrow native.
Like the one that will perform the best on ADBC.
Well, anything that can return data in Arrow format
Mhm.
is basically just going to be a pass through.
Mm.
The ADBC API will just return the pointer, the
Pointer
stuff
to
the
the arrow.
pointers, and there's no overhead in having to interpret, translate, serialize, deserialize. It can just take what it gets and send it across to you as Arrow data if the other side, if this database produces Arrow data.
Yeah. So, but I mean, does that mean it depends on the actual driver implementation then, and
Well, the
how
driver,
efficient they are moving the data into it?
Exactly. It's going to depend on your driver implementation. If the database, if the underlying data source can return data in Arrow format, then the driver implementation
It's simple.
is fairly simple. Just make the query with whatever the
push it to the network buffers. We're
whatever
done.
your protocol is, make the query and then send it through. You know, you can get like, so the Arrow Flight SQL, you know, as a protocol to interact with anything that produces an Arrow Flight SQL API interface like Dremio, InfluxDB, so on. The Arrow Flight SQL driver for ADBC is fairly simple. It implements the functions for the interface, but the results set is just forwards the results you get as is, no copy.
Yep. And one of the things I want to kind of hit on, because we've been talking about this, and I know we're not short on time, but we're starting to get towards close to the end of the show, and I wanted to make sure that we hit this. Is you're talking about a lot of open source projects that, you know, are integrating to Arrow, are having, you know, if Arrow was implemented in this project in a way where we could just pass it through, just imagine what that would perform, how things would perform. The open source community around Arrow is super important, right? So, I mean, the fact that you need driver maintainers, that you need, you know, language maintainers to have language interoperability. You need, you know, support from network clients, whether, you know, you have implementations with Netty. Having a big open source and healthy open source community is super important.
Exactly. I mean, the CI on the Arrow repo is insane because we build it in so many different environments and stuff, but we also have this massive integration testing suite that uses that IPC format, and basically for each of the official implementations,
passes it.
It basically just goes, generate it here, send it across to that implementation. Oh, read it here, make sure it got what you expected. And now do that for every combination of client and server.
Yep.
Of language, and every combination of languages. You know, Rust producing, Go consuming, C++ producing, Java consuming, vice versa, all the way around for as many types and testing and fuzzing and doing whatever we can to make sure that we maintain that interoperability, that integration promise.
Yep.
And when you start thinking about things, you know, Polars data frame library, that's entirely built on Arrow, the Rust Arrow library. But the in-memory representation of Polars is just Arrow.
Yep.
I already mentioned DuckDB's internal memory format is very similar, if not identical, to a lot of the Arrow stuff. Meta's Velox compute engine. We've ended up with new data types in Arrow from talking with DuckDB and Velox, because the two of them adopted some data types from researchers at University of Munich. And those data types got added to the Arrow spec so that we can have better zero copy integration with Velox and DuckDB.
Yep.
Yeah.
And so if you're an open source developer, if you're interested in polyglot languages, you're trying to get your hands in a lot of different spots in the code. Seems like a great opportunity, a great community to be looking at. I mean, you literally your test cases are sending from one language to another. It's like, oh, I'm a Java developer, but this whole AI thing's going on, so maybe I need to learn a little Python. great opportunity just to kind of test your language interop skills and get involved. And I know
exactly
your book, one of the favorite things I read about that is one of the last chapters that talks about open source contribution, where you basically like, you could be a college grad and you read it like you're writing like, hey, this is how you do a pull request and get commands, to this is how you interact with the community. This is how you, like, if you have a new idea, how you bring it to the message board. So you talk a lot about the people's interaction and piece to that. So I mean, like, I really appreciate that.
I made it a point for that to being the last chapter in the book, because, you know, when I was first writing the book, one of the big things that I wanted to do, aside from bringing more awareness of some of the Arrow libraries, particularly the Go library in my case, because that was my big thing, is I wanted to get more Go data science stuff. But I wanted to get more contributions and encourage that, because it's so hard for a lot of younger engineers to really feel comfortable, you know, joining or contributing to an open source project, especially one as enormous as Arrow. Like, Arrow is like, it's a mono repo for most of the implementations. So you've got one repository, one GitHub repo with C++, Java, Python, Go, Rust, not Rust. Rust is in a separate repo, but Ruby, glib. Like, you have the repository for Arrow is enormous. The CI system is insane. The build and setup is ridiculous. And it's like that because we're maintaining all of this cross-language interoperability. So, you know, you have this really intimidating project, and you come across, oh, I ran into a bug in this one spot of PyArrow.
Yep.
I want to contribute a fix. Well, how do you do that? And if you're not already familiar with the processes and the way that people interact with open source communities, it can be really intimidating.
Mm-hmm.
And so I really wanted to kind of capture that. And that's why the last chapter of my book is just entirely on getting someone from their first idea all the way through, you know, contributing it, PR. How do you talk to people on the mailing list? How do you talk to people that might comment on the PR? And getting that first contribution in. Because if you can get that first contribution in, you can get more in, because the more people we have contributing, the more people giving ideas, the better it's going to be. And Arrow as a project and as a format and as a spec lives and dies by the projects that adopt it. It is primarily, aside from the performance and benefits there, the interoperability of it being an open standard is key.
Yep.
And so it needs to be open and easy for people to feel comfortable joining the community, asking questions, because it is by no means simple to understand, and getting whatever they need so that they can then leverage it and use it in their stuff. You know, and especially as the industry is continuing to move forward, and we have, you know, as everything's moving much more towards LLMs and machine learning and AI and all stuff, and we're seeing Arrow, what we're doing with the project is trying to better make it easy to leverage those non-CPU devices with Arrow.
Yep. Yeah, having a common interchange and, like, you know, opens the door for, hey, I'm a Java developer, but all this work I did in Python, I can use it and I don't have to pay for, you know, moving it over. And I mean, to your point, that first commit, like, if you can get over that hump, like, you know, for me, it's like you kind of get hooked on it. Like, it's really fun and exciting.
That's what happened to me.
Yeah.
Like, that's how I had, like my entire journey with Arrow stuff started with, I had a project to do at work a while back. I found Arrow. I used it, saw it was really cool. Came across it was fairly early on in the life of time of it. Came across some bug, you know, a couple of null dereference bugs or other things. Made a contribution. Kept using it. Saw it was really cool. Made more contributions.
Yep.
The rest is history.
Eventually was invited to be a committer.
Yep. That's how it
Gave some
goes.
talks and then was asked to write a book.
Yeah, it's funny how that happens. But yeah, I mean, there's plenty of opportunities. Like, I mean, you've even some of the things you've mentioned, like, hey, there's a bunch of languages. Not all the languages have the same features. So like, if you're like, man, my language doesn't do this.
Yep.
Look into like, well, what would it take to do the compute in Java? Is that just some JNI bindings to the C libraries and extending it? Like, what would that take? You know, I know you mentioned a lot of the JDBC stuff is going to get close to being out of experimental mode, which is really exciting. You know,
ADBC is going to be, we're planning on ADBC hitting a actual GA 1.0 release by around June.
Okay.
Ooh.
Like right now, I would consider it, I mean, it's currently it's 0.10.0.
Yeah.
But we plan on it hitting a full 1.0, in the next couple months with ADBC, and that's the drivers and everything there.
Yep.
We at Voltron, at Voltron Data, we've been working with Snowflake to really capitalize on the Snowflake ADBC driver. There's a whole bunch of there's a group of engineers at Microsoft that have been contributing to the C# bindings for ADBC.
Nice.
You have a C# load a driver. It's the interoperability is that blows my mind sometimes, in that the Microsoft employees that are contributing the C# bindings to load the ADBC driver that exposes the C API written in Go to make requests to communicate with Snowflake.
Yep.
And the reason why it all works is because at every level through it, they speak Arrow.
There's a spec.
Mm-hmm.
You have the C# Arrow library, the Go Arrow library, the C API spec for ADBC, so on and so forth. It's crazy, but it's amazing being able to have this kind of modular, componentized setup that you can just swap out the individual parts with whatever you need, whatever library you like. Oh, I need to hit .db. Okay.
Yep.
Instead of the Snowflake driver, use .db. Now I have to hit Postgres. Well, there's a Postgres driver which just converts what it gets from Postgres into Arrow. So boom, swap it in.
Yeah. I mean, look at all the opportunities you have to interact with people, some smart people in the industry at so many different companies. I mean, that's it. I mean, if you start working in the Arrow community, you get to talk to Matt. I mean, this is great, right?
Yeah.
So
yeah. I mean, right now I'm working with NVIDIA libqdf.
Yeah.
I'm contributing back some Arrow interoperability and stuff there, because libqdf, if you're unfamiliar with it, the NVIDIA Rapids project is essentially it's Arrow on the GPU.
GPUs.
That's libqdf NVIDIA Rapids. It's Arrow on GPU. Mm-hmm. If when people talk about Spark Rapids,
yeah,
that's what they're talking about. The Rapids project is using Arrow, the Arrow format on the GPU in memory. And so currently, if you want to get the data out of Rapids, the only way to do that is, if you keep it in Arrow format, is it has to copy it off the GPU back into main memory.
Yeah.
Right.
They don't provide any way of getting the Arrow data out while leaving it on the device. That's what I'm contributing.
So you can keep it in the GPU.
So you don't pay
Fun.
that.
and what's important about that is everything we just said about the interoperability between runtimes and libraries and things for CPU regular stuff applies even more so with the GPU stuff, because one of the biggest bottlenecks to interoperability of GPU and those kind of device libraries is that it's extremely expensive to copy it off the device and then back to the device.
Yeah, you're going across the buffers. I mean, you're going across the bus and everything. Like, it's not close.
You get the best performance by minimizing how many times you have to copy it from main memory to the device and then back to main memory and then back to the device. If you minimize those copy acrosses, you get better performance.
Yep.
And so Arrow, a number of months ago, we expanded the Arrow C interface and gave it an Arrow device array object, which is basically just wraps around the Arrow array object and then provides a device ID, a device type, a synchronization event pointer if you need it, so on and so forth. And the expectation then is that the pointers, the buffer pointers in your object, in your Arrow data there, are expected to be device
dependent.
Pointers to device memory. The Arrow structures themselves are in CPU memory, but the buffer pointers are device memory. Because you still need to use the CPU to interpret and the metadata in the CPU to interpret it, but the actual raw data is still on the device. And so I have a PR up that I'm working with the NVIDIA guys to contribute going from libcuDF to those Arrow device arrays so that you can get the zero copy communication whilst keeping it on the device. And one example, I did a proof of concept of this a while back, where essentially I was using the Python number library, generated data, did some operations on it, passed it across to a C++ library with libcuDF, zero copy, just passed the device, the pointers, ran some libcuDF computations on it, and then put it back into Python
to read it out.
Number to operate on it, and finally copy it back to the host to output the result. And it stays on the device the whole time through until the end as I go back and forth in these libraries. And that means you could do this with PyTorch or just regular, or just the Torch libraries in general. If you're in Java, you can use the JNI, all those communication things as, GPU and device processing becomes more and more important. This interoperability standard
is going to be a linchpin. I can see NVIDIA having like a terabyte kind of like CUDA based cards out there already, for you to be able to do so yeah, and the little background there is GPUs, graphic processing units, are extremely good at what is called like vector and matrix math on essentially a lot of data. Essentially, it's almost like one crank of a cycle, they can do 100,000 operations at the same time. So they are essentially the linchpin of neural networks, because neural networks are essentially that 100,000 things that need to compute on every cycle. So this is going to be fun. Like NVIDIA, what is NVIDIA doing is getting it ready so that everybody can do their large language models mainstream on their own place instead of having to wait for like all these things, and efficiently as well, because then you don't even have to copy anything. You just load it up on NVIDIA and leave it there.
Now just to take advantage of the topic and plug my employer, Voltron Data, a little bit, with all the LLM stuff and all the AI machine learning stuff, all of them running on GPUs, as you mentioned, for performance, right?
Yeah.
But those things they're very data hungry. And most of our pre-processing and development stuff runs on CPU-based Spark and other things, which means they can't keep up with the data providing to those data-hungry GPU applications. And you end up with very low utilization of those GPUs. Last fall, Voltron Data, we're a startup, we went public with our main product, the Theseus compute engine, which is an accelerator native polysilicon compute, general compute engine.
I see.
So it enables you to jump over that wall, that performance wall, and get your pre-processing on those accelerated GPUs so that they can keep up with your LLMs, and you can get overall better utilization of your hardware.
Because renting a CPU is expensive, or a farm of GPUs. No, that makes sense.
Yeah. Oh, that's fun. So you get significantly faster compute, much higher utilization of your GPUs, which means lower cost of ownership.
Yep.
The whole 9 yards there. And so like just to plug Voltron a bit, since I'm here, you brought the topic up. That's where we sit here, is that high accelerator native stuff. Now, I get to work on. I'm entirely on the open source side of things, So, but like that's part of why Voltron's very heavy in the Arrow ecosystem. Because all of the interfaces and that DC engine were all built on these open standards.
And that's the beauty of it, right? Like it's so crazy when you let the genie out of the bottle and just say like, I'm just gonna leave the standard out there for everybody to take a look at, and then magical things happen, right? Like that is
exactly.
It took us a while to figure that out, but
it took way too long. I mean, it's like the old XKCD comic. We have 13 standards. We need one standard to rule them all. We have 14
standards.
It's the old XKCD comic, but
favorite.
That's what it is. You need everyone to agree on these standards, and if everyone agrees on the standards, things become modular. They become composable. And the interoperability is guaranteed. You get these, and if you watch the industry as a whole, big data systems in general in modern day now, they're becoming much more these modular, composable systems. I keep saying modular and composable, but I can't think of better words. And we're watching the old school DBMSs get decomposed into their component parts.
Yeah.
And then they become commoditized so that you can swap in and out those components to kind of build your own system, because what I'm predicting, a lot of people are predicting we're going to see, is we're going to hit a level of compute performance. CPUs really aren't getting much faster.
Yeah.
And so with things like Meta's Velox and DuckDB and Arrow Data Fusion, which is another compute engine based on Arrow and all fun stuff written in Rust and so on. But with all these things, what we're going to see that companies are going to be competing not on performance, because everyone's going to get the same performance, but on user experience and interoperability, because those individual components are going to get commoditized. Everyone's going to be eventually we're going to come to a point where everyone's going to be using this, the same basic, thing that calculates something. And throw a different UI on top. And then maybe they'll swap out the storage component. Everything's going to kind of coalesce eventually. And it's enabled by these open standards.
Yeah, no, that is kind of like you kind of see it on the hardware side, like USB-C and right, like that, and suddenly like everybody uses it, right, and you get power supplies and stuff like that. It's an interesting time for software development, because then how will that look like where I decided today, like you kind of can do it right now, but it's still like it still hurts. Like if you say I want to change a data source or a database, is still like there are things you need to do. But once everybody says like it's almost like the evolution of all these things led us to this, right? Like, and this is the most optimized ways for dealing with big data, right? There is no reason why everybody have to invent something new if what we have is the best already.
But I mean, I'm not going to claim that Arrow is the best in every scenario. It's not. If you're primarily in a transactional, workflow,
RDBMS type of deal.
Transactional workflow where you always need all the fields, Arrow may not be the best bet potentially. Definitely try the thing. But as I mentioned, how we adopted those new data types, the community around Arrow is ensuring that we stay relevant as new developments and new research and optimizations are found. Those new data types that I mentioned are run-end encoding.
Oh, really?
Not run-length encoding, run-end encoding.
Interesting. Okay, that's different.
The reason why is because is when you try to access an individual index in the array, if you're run-length encoded, then anytime you try to access it, you're going to have to sum up the lengths to find.
Oh yeah, you cannot just jump in.
If you do run-end encoding, it's a binary search.
Oh, that's okay. Oh, that's cool. Okay.
And the other data type the other bigger data types that were added was what we refer to as string view and list view. And string view is also referred to as German style strings because it came out of the University of Munich by a bunch of guys in Germany. But essentially, the basic Arrow string array is a validity bitmap buffer, a buffer full of offsets, and then one buffer with all the string data in one shot, which is very efficient to access and interact with, but does make construction a little more difficult. You can't construct it out of order because you need to know where each string starts and ends.
Right. And
string views were a way of optimizing a lot of these operations that Velox and DuckDB adopted. And what they are is a fixed size 16-byte structure that contains a 4-byte string length, the first 4 bytes of the string, and then the remaining 8 bytes depends on the size. If the string is 12 bytes or less, the whole string is inlined right there.
Got it.
If the string is longer than that, then you have a buffer offset and an index. Buffer offset and an index offset. Because you can have a variable number of buffers alongside this, which means that you can easily construct these out of order. You can point to already existing memory when you're constructing it. And that means that when you're processing one of these string view arrays, the vast majority of the time, if you're doing string comparisons, you're going to get a fast fail in that first 4-byte prefix.
Interesting.
So, Freddie, I think you made a talk probably a few years back at DevNexus where you said, hey, we're running the internet in debug where everything is efficient for the people to read, but the machines are struggling to keep up. It seems like the tides have turned a bit. We're not going to be able to human read this stuff over the internet, but it's going to be really fast.
Which again,
the machines are reading it. It's fine, right?
I like to use JSON as my example for that.
Yes, that's
like think about it this way: JSON. I have a property and I want to represent this an integer. Okay. Well, you have the bytes for the quotes. The bytes for the property name.
No, it's horrible.
1 byte per character per digit in the number, the colon. Whereas Arrow binary format represents that data,
very compact.
12 bytes.
2 bytes, 2 byte in 16 if you want, and you don't have to reproduce, you don't have to replicate the field name with everything and all stuff like that. And so we saw OpenTelemetry has adopted a Arrow format for their collectors.
Oh, nice.
And are working on getting it more throughout the full systems instead of using JSON to pass the telemetry data, using Arrow.
Yeah.
And saw 40-50% performance improvement.
Yeah.
Because the volume of data they're sending.
Yeah.
Just dropping the latency by making the data smaller and reducing that conversion cost of data to JSON, JSON to data.
Yeah.
Yep.
Yeah. No, it's Oh gosh, that could be another hour on all the gripes.
We may have to have Matt back because I know certainly we've got. I mean, we've got some code examples because we can go through some things and talk about that. But maybe we save that for the next one. I mean, I think this has been a great introduction. Like again, I think if this doesn't get you interested in Arrow, I don't know what will.
Yeah, we jumped around a bit, but that was because we wanted to cover all these things.
Absolutely, yeah.
That's one of the things I love about the Arrow project is how wide-reaching it is. You know, you've got protocol proposals, interoperability, the C API, ADBC, Flight SQL, Flight RPC, the CUDA and non-CPU integrations. Like it's there because you need all of those inroads.
Yeah.
So people will want to use it.
Yeah.
It's so funny. No. It's so good that then it's like, but what about if I keep pushing it? And that's kind of how it starts, right? Like, oh, maybe I should transfer it to the network on that way. And maybe I should use my GPU that way. And suddenly you get all these things coming in because it's like, once you're in, that kind of format is super, super easy and performant to work with. So it's
everything's better if you can have it Arrow all the way down.
Yeah, yep. It's a perfect open source project. I mean, that's why you want open source, to make it easy to adopt, low friction. Like, there's no reason not to be looking at this as something to bring in. It's like, oh, where can I put this where it's going to help me?
The hardest part is getting people aware of it, because 90% of developers will never actually interact with Arrow directly.
Well, makes sense.
The vast majority of developers are going to interact with it through other things that are built on it. You know, they interact with Arrow by using pandas or polars, or by querying Dremio, or InfluxDB Flight SQL interaction, or maybe we'll get Power BI accepting an ADBC connection. You know, maybe that'll happen sometime down the road. I don't know. That'd be freaking awesome. But like the majority of developers aren't going to interact with Arrow directly, because it is a lower level piece of the infrastructure.
Yeah, but it's still an important piece, and to float it up, like we said, like Bob said, I actually have a couple of projects where I'm gonna start looking into, will Arrow work for my multi-terabyte, like domain objects that I have.
Feel free to ask any question you have.
Yeah. And I mean, so that, and there's also, I mean, the open source project, I mean, so we didn't get into, I don't think we're gonna have time for code samples, but there are a number of code samples that show how to get started with Arrow. Cause I think that, to your point, Matt, it's not like the 3 lines of code that you would write for a Java program to read a file. There is a little bit of setup, because you got to set up the schema, access the data set, work with a column format. So, okay, we're going to do this in the field, and we're going to do this operation on the field. So there's a little bit more upfront, but the benefit that you get out of just getting over that hump and just understanding how the APIs work and the language works in the different languages themselves, you make that investment and it pays off for a long time.
And specifically, I'll say for your listeners that, with how everything has, been focused so much on, the C++, the Pi Arrow, and LLM stuff, a lot of the Arrow Java library has actually been a little bit neglected by the community, because there's just been much more in community interest in the other implementations. So it would be really, really, we're starting to, as a community, trying to push more on the Java community, because it's ironic almost, because the Java implementation was the original reference implementation for Arrow. And everything else built out of that. But then over the last several years, it's fallen a little bit behind feature-wise, and it's been harder for it to keep up, because there's just not as many Java community members that are contributing and maintaining and working on it. And so I'm hoping with this talk with you guys, with this podcast, that we can kind of reinvigorate, the Java side and the Java community to kind of take note and look more at Arrow and really jump in and get more of those contributions and discussions and, community involvement from the Java side. we are trying to keep it up to date as much as we can.
Yep.
I think the last release of Arrow, we bumped it up to using Java 21 or 22.
Okay, and that's the most recent LTS. So I mean, that's the latest version that a lot of folks are supporting. And to be frank, like you look at the benefits that it gives, there's a lot of benefits that are purely, if you're a Java developer, this is the stuff you need. Keeping stuff out of the heap, less garbage collection, all of it. Like you get it here.
Yeah, if you're working with large amounts of data in any kind of tabular, hierarchical or not.
Mm-hmm.
At a minimum, give Arrow a look.
Yep.
Yeah. All right. I think that's all we have for today. But like we said, we'll put the show notes and the links for the book in the podcast notes. And gosh, this is fun. We're back, baby. We're back.
All right. And Matt, you've got a second edition of the book coming out too.
I'm working on the second edition of the book. It'll hopefully be out around June, July, as long as I actually keep writing it. But the goal right now is getting it to the new edition out around June, July. But find me on LinkedIn, find me on Twitter. I refuse to call it otherwise. Yep. You can find me on those. I'm always reposting various Arrow announcements or otherwise. And when I do have a new edition of the book, it'll be all over those. I'm going to be at various conferences talking about Arrow stuff and also harping on this whole modular and composable idea of systems. I'm going to be at the Atlanta Cloud Conference at the end of March.
Great.
All right. Well, and that's it. Thank you so much for listening for this episode of the Java Pop House. This is Freddie signing off.
All right, this is Bob signing off, and thank you, Matt, for being on the show today.
Thanks for having me, guys. It was a ton of fun.
All right. We did it!
Hey!